Physics. I'm Mr. McConley. Today we're going to talk about what's called the general interface relationship. That's just what physics people really call it. Like, you wouldn't see that in a problem. But we're going to start with Snell's law, and I'm going to show you how Snell's law can be set equal to some other things. And it'll be very useful for you. You can use it in a variety of new situations. So the first thing you want to do here is we're going to rearrange a little bit. We're going to make it sine theta 1 over sine theta 2. And then we're going to make it n2 over n1. So all I did is I put the n's on one side and the sines on the other side. Little note while we're at this point, before we go any further. When you take the two indices of refraction and you divide them and you put n2 over n1, this is called a relative index of refraction. A relative index of refraction. And I want you to know that because sometimes that wording is used in a problem, and what they're saying is when they say they'd like to have the relative index of refraction, they're saying divide the two n values. Okay? So I'm just pointing that out so you can understand what's being asked. Anyway, taking it from here. You probably recall that when you want to find an n value, what you do is you take the speed of light and you divide that by the speed that light travels in your material. So this is speed of light, 3e8, and this is speed that light travels in your material. Well, so if we take this right here, and we apply that idea, so we got our sine theta 1 over sine theta 2, I'm going to leave that alone, but here, I'm going to plug in c over v, and specifically, it's going to be c over v2, because we're talking about number 2 here, and I'm going to make a complex fraction on the bottom, I'm going to make it c over v1, so basically I've applied this equation into the top and the bottom here. It just kind of looks like a mess, but let's simplify a little bit. If you got the speed of light in both positions on the top, they're going to cancel, right? If you got a complex fraction, you want to simplify it a little bit. Remember, you're going to do v1 over 1. That'll cancel these, but whatever you do to the bottom, you also have to do to the top. So in the end, when I get done messing around here, what do I have left? Well, I have v1 over v2. So basically what I've shown you here is that you can have the sines equal to the indices, and it can be equal to the speeds that light is traveling in that material. But we don't stop there, because there's one more relationship that I can show you. You also most definitely recall that v is equal to f lambda, right? Velocity is frequency times wavelength. And we can apply that in the same way. So I'm going to plug right in here, and I'm going to say, okay, v1 would be f1 times lambda 1, and v2 would be f2 times lambda 2. But some of you right now are getting that queasy feeling, hopefully, because what do you know about the frequency when you change materials? Oh, very good. I said a lot of people said that all at once. So really, do I have to label them 1 and 2? No, because the frequency is the same thing. And now that I take away the 1s and the 2s, what do you think can happen to the two frequencies? Cancel, gone. Bye. So what you're left with is this. You're left with that the sine of theta 1 over the sine of theta 2 is equal to n2 over n1, which is equal to v1 over v2, which is equal to lambda 1 over lambda 2. This is what we call the general interface relation, what physics teachers call. And the only thing that trips people up is that it's always 1 over 2, 1 over 2, 1 over 2, except with the n's, and the n is 2 over 1. That trips people up. Now, it's not written exactly that way in your reference table. It's written on a couple different lines. So what you need to do is check out your reference table and make sure you understand